In mathematics, a limit is the value that a function or sequence approaches as the input or index approaches some value. Limits are essential to calculus and are used to define continuity, derivatives, and integrals. The concept of a limit of a sequence is further generalized to the concept of a limit of a topological net, and is closely related to limit and direct limit in category theory. In formulas, a limit is usually denoted lim as in lim AC, an, equals L, and the fact of approaching a limit is represented by the right arrow as in an L. Limit of a function. Suppose f is a real-valued function and c is a real number. The expression means that f, x, can be made to be as close to L as desired by making x sufficiently close to c. In that case, the above equation can be read as the limit of f of x, as x approaches c, is L. Augustin Louis Cauchy in 1821, followed by Karl Weierstrass, formalized the definition of the limit of a function as the above definition, which became known as the definition of limit in the 19th century. The definition uses a micron to represent any small positive number, so that f, x, becomes arbitrarily close to L means that f, x, eventually lies in the interval, which can also be written using the absolute value sign as f, x, an Li micron. The phrase as x approaches c then indicates that we refer to values of x whose distance from c is less than some positive number ia that is, values of x within either or, which can be expressed with 0, xaci. The first inequality means that the distance between x and c is greater than 0 and that xa permil c, while the second indicates that x is within distance I of c. Note that the above definition of a limit is true even if f, c, a permil L. Indeed, the function f need not even be defined at c. For example, if then f, 1, is not defined, yet as x moves arbitrarily close to 1, f, x, correspondingly approaches 2, thus, f, x, can be made arbitrarily close to the limit of 2 just by making x sufficiently close to 1. In other words, this can also be calculated algebraically, as for all real numbers xa permil 1. Now since x plus 1 is continuous in x at 1, we can now plug in 1 for x, thus. In addition to limits at finite values, functions can also have limits at infinity. For example, consider f, 100, equals 1.9900, f, 1000, equals 1.9990, f, 10,000, equals 1.99990, as x becomes extremely large, the value of f, x, approaches 2, and the value of f, x, can be made as close to 2 as one could wish just by picking x sufficiently large. In this case, the limit of f, x, as x approaches infinity is 2. In mathematical notation, limit of a sequence. Consider the following sequence, 1.79, 1.799, 1.7999. It can be observed that the numbers are approaching 1.8, the limit of the sequence. Formally, suppose A1, A2 is a sequence of real numbers. It can be stated that the real number L is the limit of this sequence, namely, to mean, for every real number I micron 0, there exists a natural number n such that for all n, we have an Li micron. Intuitively, this means that eventually all elements of the sequence get arbitrarily close to the limit, since the absolute value in L is the distance between n and L. Not every sequence has a limit. If it does, it is called convergent, and if it does not, it is divergent. One can show that a convergent sequence has only one limit. The limit of a sequence and the limit of a function are closely related. On one hand, the limit as n goes to infinity of a sequence a, n, is simply the limit at infinity of a function defined on the natural numbers n. On the other hand, a limit L of a function f, x, as x goes to infinity, if it exists, is the same as the limit of any arbitrary sequence n that approaches L, and where n is never equal to L. Note that one such sequence would be L plus 1/n. Limit is standard part. In non-standard analysis, the limit of a sequence can be expressed as the standard part of the value of the natural extension of the sequence at an infinite hypernatural index n equals h. Thus, here the standard part function st rounds off each finite hyperreal number to the nearest real number. This formalizes the natural intuition that for very large values of the index, the terms in the sequence are very close to the limit value of the sequence. Conversely, the standard part of a hyperreal represented in the ultrapower construction by a Cauchy sequence, is simply the limit of that sequence. In this sense, taking the limit and taking the standard part are equivalent procedures. Convergence and fixed point. A formal definition of convergence can be stated as follows. Suppose S goes from to is a sequence that converges to, with for all. If positive constants and exist with. Then S goes from to converges to of order, with asymptotic error constant. Given a function with a fixed point, there is a nice checklist for checking the convergence of the sequence. 1. First check that P is indeed a fixed point. 2. Check for linear convergence. Start by finding if. 3. If it is found that there is something better than linear, the expression should be checked for quadratic convergence. Start by finding if. Topological net. All of the above notions of limit can be unified and generalized to arbitrary topological spaces by introducing topological nets and defining their limits. An alternative is the concept of limit for filters on topological spaces. See also, limit of a sequence, rate of convergence, the rate at which a convergent sequence approaches its limit. Cauchy sequence, complete metric space. Limit of a function, one-sided limit, either of the two limits of functions of a real variable x, as x approaches a point from above or below. List of limits for common functions. Squeeze theorem, finds a limit of a function via comparison with two other functions. Banach limit defined on the Banach space that extends the usual limits. Limit in category theory, direct limit, inverse limit. Asymptotic analysis, a method of describing limiting behavior, big O notation, used to describe the limiting behavior of a function when the argument tends towards a particular value or infinity. Convergent matrix. Notes. External links, Weierstein, Eric W., Limit, MathWorld. MathWords, Limit.